Alright, welcome to the video notes for today. Recently we discovered how to solve exponential equations that wound up collapsing to a system where we had a common base. For example, the very simple problem 2 to the 4x equals 16. 2 and 16 are both base 2 numbers, and so we rewrote the expression as a common base. And then from there, by using logarithms, we could cancel out the bases, and we get 4x equals 4 and x is equal to 1. Very simple problem. The ones we looked at tended to be a little more complex, but ultimately they had a common base. The question that we're going to resolve today is, how do we handle problems that have not a common base? For example, if I wrote the equation like this, 16 can no longer be expressed as a power of 2. And how are we going to resolve that? Well, we still use logarithms. It just happens that when we take the log of both sides, we are able to employ the use of one of our log properties. And one of the properties of logarithms says that if I have a log, or a natural log, of an argument raised to a power, this is equivalent to saying power times the logarithm. So this is the main property that we're going to use to rewrite the expression so that it's no longer an exponential, but rather a product. So because I took the log of both sides, this allows me to move the power down to the front by the power rule of logarithms. And my goal is to isolate the x, and so I'm going to divide both sides by 4 ln of 2. 4 ln of 2. That cancels the 4 and the ln of 2, and we get the expression ln of 15 divided by 4 ln of 2. Now certainly this is not the only approach to solving this problem. Some people would like to use the log base 2 to solve this problem, but we're going to do it using the natural logarithm. Now, I have no mental conception of what this is as a value approximately. I don't know if it's bigger than 1 or smaller than 1. So turning to our calculator, most calculators have a log button on it, and it really doesn't matter whether you type log or natural log when solving this problem here. I want to type in log 15, so log 15 divided by, and then the denominator is 4 times log of 2. And we get an answer of approximately 0.976, or if you round, 0.977. Now please note that if you're using one of the graphing calculators, your denominator should be in parentheses. If we don't include the parentheses, we will get the incorrect answer. And just to demonstrate that, I'm going to delete the parentheses out of the denominator. And we see that we arrive at a different answer. So be careful with how you use your parentheses. Okay, so let's look at that in the parent function toolkit. The problems here look a little more complicated solely because there's a upfront algebra step or two that we need to do to reduce it to a simple exponential expression. And in this case, I have the 5 subtracted and I've got the multiplier of the 4. So if I add 5 to both sides, I get 18 plus 5 is 23. And then if I divide both sides by 4, I get 23 over 4. And at this point, we've reduced it to where we can take the log of both sides. We have an exponential by itself on the left and a number by itself on the right. So let's take the log of both sides. This allows me to apply the property of logarithms where I can drop the exponent down to the front of the expression. So by dropping that exponent down to the front. I have this logarithm expression, and my goal is to isolate the x. And so the first thing that I'm going to do is divide both sides by ln of 3. Please note that the ln's do not cancel. They're not like variables. And there's no reducing of these numbers that can happen because the numbers are trapped inside the logarithm. Finally, we're going to add 7 to both sides. And then we're going to divide everything by 2 to get the x by itself. So a fraction divided by 2 and the 7 divided by the 2. Everything's been divided by 2. And this is the exact answer. It is not the only way to express the exact answer. As we get more comfortable with logarithms, I'm going to show you some more tricks that we can do to clean up what this might look like. If I were to turn to a calculator to find what that approximate value is, I'm going to build it up slowly for people who don't have the graphing calculator. So the first thing is I'm going to take log of 23/4, and I would take that number, and it's good to keep all of the decimals that we possibly can keep. So then we're going to take that decimal expression and divide it by 2 log of 3, trying to keep that in parentheses. And then to that we will add 7/2, or 3.5. We get 4.292, or if you're rounding, 4.293. Typing this all out in a singular line is possible. We could do ln of 23/4 divided by the quantity of 2 ln of 3 plus 7/2, and we get the same answer. For those who have the nicer graphing calculators, something else that's worth noticing is if you press alpha y equals, if we get that n over d expression, it's pretty nice because it creates the fraction bar for us. So it makes it easier to avoid parenthesis mistakes. Fraction 7/2. So that's a really nice feature that the more advanced graphing calculators have, the TI-84s. Unfortunately, TI-83s don't have them, and even some TI-84s don't have them. So type it in, there we go. So several different ways to type it into the calculator. When you're doing work on Kia, I oftentimes have you type in the decimal, so keep in mind the truncated or the rounded version are acceptable, and you'll want to go to 3 decimal places, which really means one of the most common ways students struggle is going from the correct answer to the correct decimal, and that's a calculator skill you'll have to work on. Okay, here's another exponential. In this case, we've got the -12, so we're going to add 12 to both sides. 14 plus 12 is 26. Then we'll divide both sides by 2. Please note that that 2 cannot be multiplied in. We can't turn this into a 10 because the exponent only applies to the 5, not to the 5 and the 2. So now that we have a single exponential on one side and a single integer on the other side, we can use the properties of logarithms to take the log of both sides and drop that x plus 3 to the front. Remember, it falls down in front because of the properties of logarithms. Then we have to isolate the x, so we're going to divide both sides by ln of 5. And finally, we can subtract 3 from both sides Now this one certainly was cleaner looking. There was no fractions to deal with, aside from this one. And it should be easier for us to type into a calculator. So log of 13 divided by log of 5. Oops, we want to make sure we use the same type of log both times. Minus 3. Okay. And just to prove it, I'm going to use log base 10, also known as the common logarithm, to see if we arrive at the same answer. And we do arrive at the same answer. So regardless of whether we use our base e logarithm or our base 10 logarithm, we're going to get to the same answer. I, like many mathematicians, tend to favor log base e. So, sorry, I don't want to say many mathematicians. I could be wrong there, but from my understanding, that's the more common approach. Okay. And that's that problem. Okay, let's take a look at the next one. I put in here a note saying recall that no exponential can equal a non-positive value. For example, if you were to think about the graph of an exponential, as it curves upward, it never equals a negative answer. So there is no input that is going to yield a negative answer. So when we solve these taking the same approach, we get to a point where we have an exponential equaling a logarithm, and at that point we can say there's no solution. Okay. The way our calculator would have handled it is if we got to that point where we were typing it into our calculator, we would have typed log of 7 divided by negative 5, and we get a non-real answer. So that's why we have no solution. So that's a reminder if your exponential equals a negative value. Okay. Add 4 to both sides and we get 0. Divide both sides by 8. 0 divided by 8 is 0. I'll just go ahead and put 0 divided by 8. And this is a non-positive value, and our exponential should never equal 0. So again, we get no solution. Now, it's not the end of the world if you continue the process. It just kind of seems like extra work, but showing that that's true, log of 0 we would have had to do, and again, we get a domain problem. So there is no solution. So, I mean, yeah. Okay. Let's do one last one, and then tomorrow we'll tackle another type of logarithm. So, subtract 5 from both sides. 8 minus 5 is 3. Divide both sides by 2. I'm just going to go ahead and write this as a decimal. 3 divided by 2 is 1.5. Then we take the logarithm of both sides. As long as we're doing the same thing to both sides, it's acceptable in algebra. This allows us to drop the exponent down in front. And then we go about isolating that x. So we're going to divide both sides by ln of 3. And then we'll add 1 and divide both sides by 9. Add 1 and then divide both sides by 9. Or divide every term by 9 is another way to think about it. So there's our exact answer. If we were to approximate that as a decimal, we could turn to our calculator and again rely on the abilities of our calculator, because I can't do logarithms in my head except for a very select few of them. So ln 1.5 divided by the quantity of 9 ln of 3, and then to that we will add 1/9. And we get approximately 0.152. All right. I think that's it. Thanks for watching. Be sure to comment, like, subscribe, smash that bell for notifications, etc., etc. Have a good day.